but I'm also happy that you are able to attend, even though we are passing through some very difficult times. We are able to conduct these programs and interact with you and keep life going. So wonderful to have you all. And you have been attending these talks for the past several days, so you all know the drill. I'm not going to repeat the process we are going to follow, assuming that you all know the process. So let me straight away start with my talk. I will stop my video and start sharing my presentation now. I'm assuming that you can all see my presentation now. Again, my name is Ramaprakash. I'm a faculty here at IUCAA, and I mostly work on building instruments for astronomy. And so most of my talk today would be about how astronomers collect data and carry out their observations. And to start with, let us try to understand what astronomy is all about, what an astronomer is typically trying to do. And most of the time, what an astronomer is trying to do can be summarized in these three Fs, F, F, and F. The first F refers to seeing the farthest objects in the universe. So one of the interesting things astronomers keep trying to do is to look at objects which are extremely far away, very, very far away, and trying to detect them, try to understand them, and try to understand their properties. As we try to do these activities to look at the farthest objects, it's also clear that the farthest objects will often be the faintest objects. Not necessarily, but very often the farthest objects are also the faintest objects in the universe. And then finally, you want to see all these objects in the universe in its finest detail, the best resolution you can get. That's another attempt astronomers make. For example, if you want to detect a planet going around a star, given the orbital dimension of the star, of the planet around the star, and the distance to the star, you can see that the separation between the planet and the star as we see from Earth would be extremely tiny, very, very tiny angle. So if you want to separate the star from this planet in either spectroscopy or imaging, you need to get to very fine telescopes which are able to see very fine details. So in a nutshell, what astronomers typically are trying to do are to see the farthest objects, which are also very often the faintest objects in the universe, and see them in the finest detail possible. So that's the whole game of astronomy. So let us try to understand how this is achieved. I will not take it into too much of a technical discussion, but I'll keep some equations in the slides so that you understand the relations between different parameters and how they are interconnected. So before getting into this, let me clarify one thing. We are today going to talk about only a very small part of the electromagnetic spectrum. Although astronomers use the entire wavelength range from thousands of meters to 1 part in 1,000 of a nanometer wavelengths to study the observable universe, we are concentrating today in a narrow wavelength region, which is very close to the visible wavelengths, slightly longer than visible wavelength in the infrared and slightly shorter than visible wavelength in the ultraviolet. The reason we are concentrating on this is as you want to observe light at different wavelengths, your technology has to change. So each of these different wavelength bands would require different technology for collecting the radiation and observing. So optical telescopes are used, the so-called optical telescopes are used to collect radiation from near the visible light, from roughly very close to the infrared wavelength to very close by ultraviolet wavelength. Something like 2 to 3 micron wavelength, all the way down to something like 200 nanometer, 300 nanometer wavelength. So 300 nanometer to less than 3 micron. That's a wavelength range we are going to talk about today. Of course, you would have discussions you would have listened to where people observe at other wavelengths like radio, X-ray, gamma rays, etc. We will not touch on those wavelengths for today. Now, coming back to optical telescopes, let me ask this essential question, because a telescope is an astronomer's main tool. Now, what do a telescope do for an astronomer? If you ask that question in a simple-minded way, the answer would be telescopes bring objects closer. That's very obvious. You look through a telescope, a distant object appears closer to you. Now, let us try to understand that in a little bit more detail in the context of astronomy, for example. Bringing an object closer has two aspects. When an object appears to be closer to you, you are beginning to collect more light from that object, and you will see more details of that object. A candle which is very far away, you may not even be able to see the light from it. But as the candle appears closer to you, you will start seeing light from it. You start collecting more light from the candle and you start seeing it. Similarly, a person standing very far away, you wouldn't know who it is. But as a person comes closer to you, you start seeing more details, and then you can understand who that person is, what properties are, and so on and so forth. So the telescopes bring objects closer, which means it allows you to collect more light from the object and also allow you to see more details. Now, the aspect of the telescope which allows it to collect more light is the diameter of the objective of the telescope, or the primary objective, primary optics of the telescope. The larger the diameter, you collect more light from a distant object. The ability of a telescope to see fine details, more details, is defined by its focal length. So diameter defines how bright an object becomes when you look through a telescope. Its focal length defines how much more details you can see as you look through the telescope. Now, to put this in perspective, when the first telescope was used to do some kind of astronomical observations by Galileo Galilei, about 400 years ago, his telescope had a diameter of about 40 millimeters. But today's largest optical telescope has a diameter of 10 meters. Compared to Galileo's telescope, it is very, very large. Similarly, Galileo's telescope had a focal length of about 400 millimeters, but Keck telescope, the largest existing optical telescope, has a focal length about 150 meters. So from Galilean times, we have come a long way. We have improved our technology, in able to collect more light, or able to see fainter and fainter objects, and also see them in finer and finer details. In both these aspects, we have, over the past 400 years, improved our capabilities substantially. Now, we said that telescopes bring objects closer. Now, to understand this a little bit more, we need to understand what the distances we are talking about in the universe. How far away are typical objects? What are the kind of distances we are talking about? And what kind of units do we use to measure them? So that's what I would cover in this slide, a quick introduction to astronomical distances and its units. Because distances to celestial objects are very large, astronomers use different units rather than meters or kilometers to measure distances to distant objects. And one such unit, as many of you know, is an astronomical unit, which is nothing but the mean radius of Earth-Sun distance, or mean radius of Earth's orbit around the Sun. So if we all know that light takes about 8 minutes to travel from Sun to Earth, so 8 minutes times 60 is the number of seconds it takes. And we know the velocity of the speed of light, which is 3 × 10⁸ meters per second. So the total distance, which corresponds to one astronomical unit, is roughly 1.5 × 10⁻11 meters. So you can see that it's a very, very large distance, which is the radius of the orbit of Earth, mean radius of the orbit of Earth around the Sun. Astronomers use a different unit, which we all know about, which is called the light year, the distance traveled by light in 1 year. So if there are 3 × 10⁷ seconds in 1 year, and light travels 3 × 10⁸ meters in 1 second. So 1 light year is about 10⁻16 meters. So it is 10⁵ times larger than one astronomical unit. Astronomers typically use even a larger unit to measure distances. Let me try to quickly explain that. To understand that, let me show this diagram where I've drawn a straight line here. If I draw 2 lines from the edges of that straight line converging at a point, now there is an angle subtended by these 2 lines. If I make this same line, same stick, farther away from me, I'm sitting here looking at this stick. So the 2 lines which are drawn from the edges of this stick converge and subtend an angle in my eye. If I move the stick farther away, this angle becomes small. And further away, this angle becomes small, even smaller. So if I take a stick, which is 1 astronomical unit in size, that is 1.5 × 10⁻11 meters in size, very large stick, how far do I have to go so that the angle subtended in my eye is 1 arc second? For those of you who do not know, 1 degree can be divided into 60 arc minutes, and 1 arc minute can be divided into 60 arc seconds. So 1 arc second is 1 in 3,600 of a degree. So it's a very, very, very tiny angle. So this distance has to be enormous, because this stick is very large. And if this stick has to subtend that tiny an angle, as tiny as 1 arc second, you have to go very, very far. And that distance is called 1 parsec. And it is relatively easy to show that 1 parsec is 2 × 10⁵, that is number of arc seconds in 1 radian, 2 × 10⁵, times 1.5 × 10⁻11, which is the size of the stick. So this is nothing but, for calculating this distance, you have to multiply this distance by the angle. So the angle in radians multiplied by angle in arc seconds converted to radians multiplied by that stick size. So that is about 3 1/4 times light year. And that distance is called 1 parsec, usually written as 1 pc. So astronomers very often use a parsec as a unit of measurement. It is about 3 1/4 times a light year. Now, if I take the nearest star from Earth, from the Sun, it is called Proxima Centauri. Proxima Centauri is about 4.2 light years away, or about 1.3 parsecs away from the solar system. So if I put Sun here, the nearest star is about a parsec or so away. So this is typically the interstellar distance. If you take any 2 stars, typically they are separated by a few parsecs apart. And that is why parsec is a very convenient unit. Or similarly, they are separated by a few light years apart, because a parsec is nothing but 3 1/4 light year. Now, if I take the nearest, the size of the Milky Way, our galaxy, the size of the Milky Way is about 20,000 parsecs. So if interstellar distances are typically 1 parsec, few parsecs, size of our galaxy is 20,000 times larger than that. So Milky Way is an enormously large structure compared to typical distances between stars in the galaxy. If I take the nearest galaxies, which are dwarf galaxies going around our Milky Way, called Magellanic clouds, there are two of them, large Magellanic cloud and a small Magellanic cloud. They are about 50 kiloparsecs away. The nearest large galaxy, called Andromeda, to our galaxy, Milky Way is our galaxy, Andromeda is the nearest galaxy, which is not a dwarf galaxy, it is the nearest big galaxy. That is about a megaparsec away, 0.6 megaparsec, or almost 1 megaparsec away. So you can see that interstellar distances are of the order of parsecs. Size of the galaxy is of the order of several kiloparsecs. And the distance between galaxies is a factor of 1,000 larger. It is about a megaparsec or a few megaparsecs. So galaxies themselves are separated from each other in megaparsecs. If I take the size of the visible universe as we can see today, it is another factor of 1,000. It is 4 gigaparsec, 4,000 megaparsec. So you can see that interstellar distances to size of the galaxy, to size of the distance to the nearest galaxy, to the size of the visible universe, each stage you are adding factors of 1,000. And already these distances of 1 parsec, etc., is enormous. So our universe and the celestial objects in the universe are distributed in a very, very, very vast space. And sitting on Earth, we are trying to peer at these objects through our telescopes. And we say that one of the things which the telescope do is bring objects closer. So these are enormous distances. So what is bringing an object closer mean when objects are really almost infinitely far away? They are not small distances compared to the size of the telescope, diameter of the telescope, etc. Focal length of the telescope, they are enormously far away. So what does it mean by saying telescope bring objects closer? Now let us try to understand that in the next slide. How does a telescope work for an astronomer? How does a telescope bring an object closer in this sense, if they are so far away? Now to understand that, you have to decompose again, as we saw in the first slide. Bringing an object closer means two things. Make that object brighter and allow you to see fine details. So let us try to understand how that works in the context of astronomy. So to understand that, first I put a star here at the right top corner. You see a black star, and light is radiating away from that star. So these spheres which I have drawn are just the distances which the light reach at a given time. So the light starts from the star and radiate away in all directions, expand away in a spherical wavefront. And at a given time, it will wavefront light which have started from here. After a given time, it would have reached here. And some more time, it reaches here, and so on and so forth. So it's expanding away, spherically expanding away from that star. Now, if as we discussed in the previous slide, these distances, if I am sitting here on Earth, these distances are enormous. Even for the nearest star is a parsec away, which is several light years away. So given the size of the star, the size of the Earth and solar system, etc., these are huge distances. So what happens is, if I sit here on Earth and observe that star, while the rays from that star are emanating radially away from the star in all directions and expanding away as spheres of equal phase, as they travel these enormous distances, this curvature of the sphere has become very, very tiny. because this is almost become a sphere of infinite radius. So a sphere of infinite radius is just a plane. So what it means that the rays which started off from the star radially away are arriving on Earth and falling on our telescope as parallel beams. They are not diverging beams, they are arriving parallel to each other because these distances are enormous. They are very, very large distance, so that the curvature of this surface of the wavefront is so tiny, it is almost like a plane. So the wavefronts are almost parallel to each other. So that's a key thing. Now, if I keep a telescope here, and which is primary objective, optics is this size, I'm collecting light from this much area of that sphere. Now, if my telescope's primary objective is this large, I'm collecting light from that much area of that sphere. And that means the bigger telescope, with a larger diameter, make this object appear brighter. It is collecting more light from the sphere which is expanding away from that. So the diameter of the primary objective optics of the telescope defines how bright an object becomes. A tiny telescope will collect light from only a small part of the surface, while a large telescope will collect light from a large part of the surface, thereby making the same star appear brighter to you. So that is part one, how a telescope make an object brighter to you. Now, the second part is, how does the telescope allow you to see fine details? To understand that, let me put a second star right next to the first star. Now, if you're sitting here, the light from both of these objects, the black star as well as the red star, would be arriving at the telescope together. If the telescope is somehow able to distinguish or separate the light coming from the black star from the light coming from the red star, then it will see them as two different stars. If it cannot distinguish the light arriving from the two stars here and see it all together, and it is not able to separate them, the telescope will see these two stars as one blob of light. You will not know, observing from that there are two stars there. That detail is lost, that resolution is lost. You are only going to see that there are one blob of light. Now, how does this work? Now, how does the light from this star arrive on Earth? To do that, I have to draw similar spheres, and those spheres expand away. But now, the red surface here, although it arrives on the telescope along with the light from the black star, this surface, although it is very plain, close to plane surface, it is centered on the red star, while the black surface of wavefront is centered on the black star, which means the rays which are arriving on Earth from the red star arrives at a slightly different angle compared to the rays which are arriving from the black star. So if the telescope is able to distinguish or separate these two, the rays coming from the black star in this direction and the rays coming from the red star at a slightly different angle, and if the telescope is able to distinguish these angles, it will allow you to see these two stars as two stars. And otherwise, if it's not able to distinguish this angular separation between the rays, it will see this as one blob of light, and that detail is lost. So that is how the telescope, that is how it defines whether the telescope is able to see them fine details or not. And the property of the telescope which allows you to distinguish this angle of arrival from the two objects is the focal length of the telescope. So let us try to understand that a little bit more in this ray diagram. It is a very simple ray diagram. Let us represent the telescope by an optics shown like this, just a lens. This is your telescope. So if you are pointing this telescope to a star infinitely far away, light from the star, all the rays from the star appear parallel and reach this lens, reach your telescope. And you all know from 10 standard ray optics that they will all converge to the focal length of the focal point of the telescope on axis, because this is pointing directly to the star. Now, the diameter of the telescope, as I said earlier, would define how bright that object appears to be when you look here, how much light arrives here from that star. If there is a second star, the red star, the light from that star arrives at a slightly different angle from the first star. Of course, from ray optics, we know where that light will go on the focal plane of the telescope. They will converge to a point which is below the optic axis. So the rays, all the rays from the red star are converging here and forming that image. From the first star are forming an image here. So this separation between the two images formed on the telescope focal plane is defined, if that separation is defined as h, and the angular separation of the objects in the sky, this angle, that's the same as this angle. If that is defined as theta, we know that h is equal to f theta. So h is equal to f theta. So focal length of the telescope for a given angular separation on the sky defines how linearly separated these two images are at the telescope's focal plane. Now, if this linear separation is too small, we will not be able to see the two stars as two stars. If the linear separation is large enough, like this, you can see the two stars as two stars, and you are resolving that object. So this linear separation is defined by nothing but the focal length of the telescope. So in the way that f theta is equal to h. So for a given angular separation of two objects in the sky given by theta, the linear separation h over f is the angular separation you can in radians, which you can resolve. Now, if you convert that into arc seconds, there are 206,265 arc seconds in 1 radian. And if we define plate scale as the angle in the sky p, which provides 1 millimeter linear separation at the telescope plane. So plate scale p is given by 206,265 by f, which is f is in the focal length in millimeters, that many arc seconds per millimeter. So if we know the focal length of the telescope, you know per millimeter separation at the focal plane, what does it correspond to angular separation in the sky. So that is just a focal length property. So this is how the diameter of the telescope allows you to see brighter and brighter objects. The larger diameter, the more light it collects. And the focal length of the telescope defines how well separated the images how well are on the telescope's focal plane, and therefore how much detail you are able to see with the telescope. Now, we have described the telescope in the previous slide as just a lens. Very often you need more than one optics component to create a lens. For example, here there are two lenses which are forming the objective of the primary optics of the telescope, and the parallel beams converge at the focal plane. Either you can put a detector here, or you can put an eyepiece to look at that object with your eye. So this is a refractive telescope. Very often, telescopes are not made by lenses with refractive elements. The light passes through and bent due to the refraction property of the material, but you use reflection to build telescopes. So the Newtonian reflector is just a parabolic mirror, primary mirror. Light arrives from the distant objects on the mirror, gets converged by this concave parabolic mirror. And instead of letting the light focus somewhere here, you put a fold mirror here, a flat mirror, and let that the light focus here, just for convenience. Similarly, the Cassegrain telescope, the primary mirror is a parabola, and then there is a convex ellipsoidal secondary mirror. So the light arrives here from the distant object, converges toward the secondary mirror. Secondary is convex, so it actually does not allow the light to converge immediately. It expands a little bit so that the light converges behind the primary mirror through a hole in the middle. And then you can put your eyepiece there or your instruments there to carry out analysis of that light. And similarly, so on and so forth. There are various different kinds of optical arrangements by which the telescopes can make. But most of the current telescopes are made of the Cassegrain reflector type, and also of Schmidt or Maxto catadioptric arrangement. The telescopes are either of these types most of the time nowadays. Now, if I want to put a telescope and observe the sky is not a fixed target. Sky is a moving target, because the Earth rotates around its axis, and the Earth is also rotating around the sun. These two movements make the sky appear to move with respect to the Earth. Sit in the Earth and observe the sky appears to move. So if the telescope has to look at the target in the sky, it has to track that object. And in order to do that, telescopes are mounted in various kinds of tracking arrangements. One of those arrangements is this alt-azimuth arrangement, where the base platform of the telescope is horizontal. And then on the horizontal base, you have an arrangement where the tube of the telescope is mounted so that it can move along this axis, which is the altitude axis, up and down, or this axis, which is the azimuth axis, around in different directions, east, west, and so on. Another arrangement is which is called the equatorial arrangement, where instead of keeping the base horizontal, the base is kept in an orientation which is, in a way, this direction points directly to the celestial pole, North Pole in the case of Northern Hemisphere and South Pole in the case of Southern Hemisphere. Which means this angle from the horizontal to this is equal to the latitude of the place. So if the mount is designed like that, then the telescope, again, is a structure in which the other axis is fixed, and the axis around which the telescope can move up and down. And the advantage of this is because this is arranged in a way that it matches with the way Earth rotates. The Earth rotates around its axis. So the telescope's axis, one of the axes, is also pointing toward the pole of the Earth, where the Earth's axis is pointed. It is relatively easy to track objects in the sky with this kind of mount. So both kind of mounting arrangements are used in telescope systems nowadays, but more and more people are building telescopes in alt-azimuth mount systems nowadays. So now I'll just do a quick slideshow of some of the astronomy sites around the world. This astronomy site is on top of Mauna Kea in Hawaii at a height of about 4,200 meters above sea level. So these are the twin Keck telescope, the largest telescopes existing in the world now, each of them 10 meters in diameter. The primary mirror of the telescope is 10 meters in diameter. This is the Japanese Subaru telescope, 8 meters in diameter, the Gemini telescope, 8 meters in diameter, and so on and so forth. So the largest, many of the largest existing optical telescopes in the Northern Hemisphere are on top of this mountain called Mauna Kea in Hawaii. This is just a close-up view of the two Keck telescopes. You can see the primary mirror of the telescope, which is 10 meters in size, each of them, and there are two of them identical. This is another marvel of a telescope, which is a 5-meter diameter. The size is about 5 meters, 200-inch telescope in Mount Palomar. So you can see this height is roughly one human being. So you can see the enormity, or the door size is one human being size. You can see the enormity of the structure. This is a 5-meter Palomar telescope. This is a 4.2-meter William Herschel telescope in Spain. These are 4 identical telescopes in the Southern Hemisphere. Each of them are 8 meters in diameter. So this is an 8-meter diameter telescope, and 4 of them, they are called the Very Large Telescopes, or VLTs, and they are in the Southern Hemisphere, and so on and so forth. So this slide just quickly shows some of the largest telescopes existing in the world now. These are 4-meter diameter telescopes. Blue ones are in the Northern Hemisphere of Earth. Yellow ones are in the, orange ones are in the Southern Hemisphere. So these are 4 meters in diameter. These are 8 meters. These are 10 meters in diameter, and so on. And some of the telescopes are set up as twins, like the Large Binocular Telescope or the Keck 1 and 2 telescope, or in 4, VLT 1, 2, 3, 4, very large telescope. Now, astronomy is moving forward. This is these Keck telescopes and the largest existing telescopes were built more than a decade ago, more than 2 decades ago, some of them. Now we are in a phase we are going to build the next largest telescopes. And so this is one example. This is called the Giant Magellan Telescope, which has a diameter of about 24.5 meters. And it is made of 7 8-meter diameter mirrors. So you have, this is 8-meter diameter. You put 7 of them together to form one telescope, which is roughly 24 meters in telescope. And the light combines together and is imaged at the back of the primary mirror through this hole. This is an image of the 30-meter telescope. The diameter of the primary mirror is 30 meters. So it is made of hexagonal segments. You can see here each hexagon. There are about 500 hexagons arranged together to form a 30-meter diameter surface. And India is part of this project where we are, it's an international consortium which is building this facility, most probably in Hawaii again. And it is partners are India, China, Japan, Canada, and 2 universities in US, Caltech and University of California. So these institutions in these places are building this project, most probably in Hawaii. And its diameter is 30 meters. And this is another example, which is the European Extremely Large Telescope going to come up in the southern hemisphere. Its diameter is 39 meters. Again, made of hexagons. You can't see the individual hexagons here because it's just too tiny. But it's made of about 1,000 hexagons, 1,000 hexagonal pieces, each of about 1.4 meters in size, forming a large 39-meter surface. So if I go back to this slide and put a circle here showing what is the size of the Keck telescope, currently indicative size, the European Extremely Large Telescope is going to be very, very large compared to that, which means the light gathering power, the ability of our astronomers to collect light and see fainter and fainter objects is going to be enormously improved when these facilities start becoming operational. So, having said that, let me try to kind of quantify how faint an object we can see in the sky. We said the telescopes are made larger and larger to see fainter and fainter objects. Now, is there a limit to this? How faint? What is the faintest object you can see? If you make telescope bigger and bigger, can you continue to see objects which are fainter and fainter and fainter, and there is without any limit? Or is there a limit? So that's what I'm trying to address in this slide. So the question is, can we see objects fainter than the sky? So for example, if I go out and look at the sky now, you don't see any stars. That is because the sky is so bright that all the stars which are much fainter than the sky are not visible to you. It's not that the stars are not there. They are there, just like night time, they are there even during daytime. We are not able to see because the sky is so bright. Now, I'm trying to illustrate that by something here. This is just a patch of the sky. I put a star at that patch of the sky, which is this bright. Now, if I make that star fainter, and fainter, at some point you don't see the star because the sky light is brighter than the star light. You stop seeing that star. I'm just going to make the sky a little fainter to make sure that you know that the star is there. So when I made the sky darker, the star appears there. So it's not that I use PowerPoint to remove the star from there. It is just that the sky was so bright early, you don't see the star. If I make the sky darker, the star is still there. So if the sky is very bright, clearly you cannot see stars. So is sky the limit of what you can see? Now, you don't give up like that. You say, okay, I know how much light is coming from the sky. I just go here and measure how much light is coming from the sky. I measure here and I look at this direction and measure how much light is coming from this part of the sky, which includes the light from the star as well as the light from the sky. Whatever I call sky is just the background. It may not be the sky brightness. It could be just the city light scattering back from the atmosphere. Any light other than your target, the stars, which is coming from the same direction as your target or the star you want to observe, is for this purpose called the sky or the background. So if the city light is so bright and the atmosphere scatters back a lot of light from the city lights, you will not see stars in the sky even at night. So what is called sky is the background or the light coming from the direction of the star, but is not coming from the star, but from other sources, the contaminating light. So if I measure the contaminating light from the sky or the background in this vicinity, and then measure the total light coming in this direction, and subtract this light from this light, you should be able to see the star. Because if there are 101 photons coming from this direction, and only 100 photons coming from this direction, 100 units of light coming from this direction. So that excess light, when you subtract off, you should be able to see the star. Now the question is this going to work? Is this technique going to work? Yes and no. That is because every time you make a measurement of the light coming from any source, does not mean the sky itself or the star itself, any light measurement, there is an error in the measurement. Your measurement is never going to be perfect. There is always going to be an error in the measurement. So the question is, how well can you measure the sky brightness? So the rule is, if you collect n photons from any source, photons are just units of light or packages of energy. So if you collect n photons from any source, there is an inherent uncertainty of root n. The error in that measurement is root n. So you can only say that I collected n photons plus or minus root n. That is my uncertainty. That is the error in my measurement. This is not because of any technology error. This error is not introduced because of any limitations of your measurement system. This uncertainty is coming inherently from the nature of photons. Because if you take an object which is emitting light, there is no reason to assume that any given interval of time, it is emitting exactly the same number of photons. Even if the sun is steady, it is not changing. The star is steady, it is not changing, or the galaxy is absolutely not changing its brightness. On an average, during any given interval of time, it need not emit exactly the same number of photons. The emission of photons is a statistical process. So any given time interval t, the number of photons coming up from that source would vary. In different experiments. You would repeat the experiment multiple times, measuring light from that same object. For a given interval of time t, you will get different number of photons, because the emission of photons is a statistical process. So if the nature of the statistics is such that if I collect n photons from a target, it has an inherent variation, inherent uncertainty, inherent error of root n photons. So if I measure the light from this part of the sky and I collect 100 photons, I know that measurement is uncertain because of the nature of photons. I know that measurement is uncertain to an extent of 100 plus or minus 10. So I know it's only to that extent. So if I collect 1,000 photons from here, that measurement is accurate only to the extent of 1,000 plus or minus root 1,000 plus or minus 33, for example. That is the accuracy I can get. So if I have 101 photons coming from this star, it is already uncertain to an extent of root of 101. Now, if I subtract the sky, which is only emitting 100 photons from this part, which again is uncertain to plus or minus root 100, which is 10, the uncertainty in these two measurements is so larger than the signal of the star, which is just one count compared to the sky. It is only one count extra. So you are not able to detect for sure whether the star is there or not. So I'm trying to illustrate that quantitatively here in a table. So there are 5 columns in this table. First column is the number of photons you collect from the star. The second column is the number of photons you collect from the sky. Sigma star is nothing but the square root of this. Sigma sky is nothing but the square root of the number of photons you collect from the sky. And the signal to noise ratio is nothing but the signal, which is the photons you collect from the star, divided by the total noise. The noise from the star, noise from the sky added in quadrature. I will not explain why it is added in quadrature and not just summed up. But let us take that the total noise is always calculated by adding the individual noise in quadrature. Square them, add them, and take the square root. So this is the signal, this is the total noise. So signal to noise ratio is the ratio of that. So if the signal is much larger than the noise, you will be able to see the star. If the signal is smaller than the noise, you will not be able to see the star. So let us take this equation where the star is emitting only one photon in a given time. The sky is emitting 100 photons in a given time. So the uncertainty in measuring this is 1, because this is known only to 1 plus or minus root 1. This number is known to an uncertainty of 10. So 100 plus or minus root 10. So you plug in these numbers in here, because sigma star is very small compared to sigma sky, can be neglected. And the signal to noise ratio is about 1 by 10. This is 1 divided by 10. We plug it in here. So the signal is 10 times weaker than the noise or uncertainty in your measurement or the error in your measurements, that you are not able to detect the presence of that star there. On the other hand, if I make a larger telescope, which is able to collect 100 times more light, so you get 100 times more light from the star, but you also collect 100 times more light from the sky, because the telescope doesn't know whether light is coming from a star or sky. So this is collecting 100 times more light from the sky. But the error in this is 10, error in this is 100. If I plug that back in here, signal to noise ratio is 100 over roughly 100, because 10 squared plus 100 squared, square root is roughly 100. So 100 over 100, my signal noise ratio has become 1 now. Which means if you have a big telescope, even if the star is 100 times fainter than the sky, you can detect, you can almost detect it, because signal is equal to the noise here. Now take a bigger telescope, or you collect light from the same star for 100 times more duration. Your exposure time is 100 times longer. You keep the telescope pointed at that star and collect light for a longer duration, so that your N from the star, the total photons you collected from the star, is even 100 times larger. Of course, the sky also becomes 100 times brighter, but now the error from the star measurement is only 100. Error from the sky measurement is square root of this, which is 1000. Now the signal to noise ratio is 10,000 divided by 1000, which is 10. So what it shows is that even if the object of the star is 100 times fainter than the sky, if you collect sufficient number of photons, the signal from the star can at some point become larger than the total noise, and therefore you will be able to detect the star. What you are trying to say is the star is producing from here 1,000,000 plus 10,000 light is the total photons you can get from this direction. 1,000,000 photons you get from here. Each has this uncertainty, but that uncertainty, total uncertainty, is still smaller than the total light, extra light coming from the star. So when you subtract it off, you know for sure that this extra light is coming from an object and not a random fluctuation of your signal measurement itself. So that is how bigger and bigger telescopes allow you to see fainter and fainter objects, because the error in measurement only scales like root n. So if you collect n photons, you can measure them with a root n uncertainty. Now, so that is first part of the talk. I've said the telescopes allow you to make objects brighter or allow you to see fainter and fainter objects. And the other part is, and then we have understood that the property of the telescope which allows you to fainter and fainter object is the diameter of the telescope or the collecting area of the telescope. And we found that if we collect a certain number of photons, there's a certain number of inherent error in that measurement. And by collecting more and more photons by using bigger telescopes or staring at the same object for longer duration and collecting more photons, you can make the uncertainty or your error in measurement as a fraction expressed as signal to noise ratio small enough that you will be able to detect the object. So I will stop there for today because we have finished our time. And tomorrow we will talk about the other aspect of the ability of the telescope, which is its ability to see finer and finer details, and how fine details you can see in objects, what are the limitations to that, and how astronomers overcome those limitations. That is what we will discuss in the next talk. Thank you very much. Now I will be able to take some questions now. For that, let me stop sharing for now and look at questions if you have any asked. So if you have any questions, some of you I can see have asked questions, so I will try to answer some of them. And some of you might have asked questions. Some of you are watching YouTube might have asked questions on that channel. Let me try to answer those questions also eventually, but let me first address the questions which have come by chat. So first question is from Arjun Dawn, who is asked, there are 3 types of reflector telescopes. Can you explain the advantages and disadvantages of them with respect to each other? Yes. So I have only shown 3 types in my slides, but there are many, many different possibilities, and each of them have different advantages and disadvantages. So let me just say what the advantage of the Newtonian telescope is. Let me try to share my screen here and go to that slide. I will not make it full screen for now, but let me go to this slide. So you can see the Newtonian telescope. The main advantage of this telescope is it is just one mirror. That is the main optics. This is just a flat mirror which folds the light in this direction. It's not really doing anything special. So this is only a very simple optical arrangement where it has only one mirror. Now the main disadvantage is if you see this mirror here blocks the light which is coming in, and it is only you can see it only through the side. And if I want to get a focal length of, let us say, 10 meters with this telescope, the tube of the telescope has to be almost 10 meters in size, which is very difficult to make. On the other hand, if I fold the beam like this with the secondary mirror here and bring the beam back out here, like in the Cassegrain reflector arrangement, the effective focal length is from here all the way to here and back to here. So it is like a binocular folding the beam back and forth so that the effective focal length can be much larger than the physical size of the telescope. So most of the modern telescopes use some kind of beam folding so that the physical size of the telescope structure can be smaller, much smaller than the actual focal length you can achieve. And that is true in this arrangement also. So most of the modern telescopes have at least 2 mirrors. Many of them have more than 2 mirrors. and they fold the beam in a way that the focal length can be much larger than the physical size. So that's the main advantage between the old Newtonian system, which is very simple to do and make, versus the new system, where the surfaces can be paraboloid, ellipsoid, and in this case, a more complicated shape. But the advantage is the telescope structure can be much smaller. So let me stop sharing now and get back to the next question, which is somebody is asking, will you be sharing the slides too? I guess you're asking whether I will be making this available to you. One way of doing that is this video is available on YouTube. You can contact us and this talk can be made available to you. And if you really want to get the slides themselves, please write to me and we will see whether I can share the slides with you. So the third question is, Chirag Advani has asked, does the standard deviation equal square root of n mean that we fit the data on a Gaussian? If yes, then there is a random walk process behind it. Okay, so standard deviation equal to square root of n or square root of mean does not mean that it is always a Gaussian, but then a Gaussian can have a standard deviation which is equal to the square root of the mean. The more appropriate probability distribution for distribution of the photons is the Poissonian distribution. The Poissonian distribution is the one in which the standard deviation is equal to the square root of the mean. Now, when for large number of photons, the Poissonian becomes more and more look like or closer and closer to Gaussian. So Gaussian approximation very often would work, but the exact probability distribution is a Poissonian, which is where the standard deviation is equal to square root of the mean. Now, second part is this a random walk process? That is what I tried to explain it. If you think of let us take the sun. So the way sun produces light is by some thermonuclear processes at the core, where hydrogen is converted to helium and the excess energy comes out. Eventually, part of it comes out as radiation. Now, this is just a statistical process. So in any given unit of time, it does not mean that exactly the same number of hydrogen atoms combine to become helium atoms and exactly the same number of photons come out from the surface of the sun. That's not true. It's just a random statistical process. All that we can do is that for the nature of the radiation which is coming out from the sun, which is like a thermal radiation or black body radiation, you can show that the statistics associated with the emission, the variation in the emission from time to time is scales like square root of n. Then the next question is about which telescope would be better, of large resolution or of greater magnification or somewhere between. Now, there is no unique answer to this. This depends on what you want to see or what kind of astronomical observations you want to undertake. So if you want to undertake, let us say, a study by which you want to see the galaxy, a given galaxy in great detail. You want to resolve fine structures in the galaxy, its arms, into and each of the arms into star-forming regions, and so on and so forth. You want a telescope which has very high, very big resolution, very good resolution, a very large focal length. But on the other hand, if you want to carry out a very large survey, you want to measure the brightness of stars in all the sky in as short a period of time as possible, then you might want to design a telescope which is a very wide field of view, but very small resolution. The resolution is not good, but it can cover large area in the sky. And therefore, you can cover, complete the survey in as little time as possible. Similarly, if you are looking for extremely faint objects in the sky, you design the telescope in a way that it collects, its diameter is as large as possible. You are not very worried about the focal length. So depending on what you want to study, you would choose the appropriate telescope. So all telescopes are not same. They have each different telescopes are different capabilities, and you pick the right telescope for your particular study you want to carry out. Can you please repeat the calculation? How plate scale calculation comes as 206,265 by F arc seconds per millimeter? I'll try to explain this quickly by sharing my screen once more, but you should try to do it yourself anyway. So I hope you understood that F theta is equal to H. That is nothing but the distance times the angular size is equal to the linear size here. So F theta is equal to H. Now you can rewrite that as theta is equal to H by F in radians. So the angle here is equal to H by F in radians. Now, if I ask what theta will give 1 millimeter of H, then I have to substitute. So instead of theta, I write this as P. 206,265 is the number of arc seconds in 1 radian. So 2 pi radians is equal to 360 degrees, or pi radians is 180 degrees. Now 1 degree is 60 arc minutes. 1 arc minute is 60 arc seconds. So if you put it all together, you will find that there are 206,265 arc seconds in a radian. So, and that arc seconds in a radian divided by that F expressed in millimeter will tell you the plate scale in arc seconds per millimeter. Hope that is clear. Just go back and work it out and it will be obvious to you. Now, the next question is, considering Earth rotation, we need to rotate the telescope, but there is a limit in rotation of telescopes. So how do we manage to observe a particular target for a long time? Yes, there are many limits. I will try to illustrate some of this in my next talk. So Akash, please hold on to your question. If the answer is not clear after my next talk, please ask me again. I will address this point in my next question, my next talk. There is a question about what is the use of optical filter, how it helps in observation, how to make filter for solar observation at lab. Okay, so I talked about telescopes which allow you to collect light over its primary objective and bring them, it is focused at its focal plane. Now the whole game of astronomy is, what do you do with that light? If the light is focused by the telescope at its focal plane, you have to analyze that light in its various properties. And by that proper analysis is what we try to understand. We get information about what is the nature of the celestial object which is emitting that light is. And that analysis can be various things. How the light is varying as a function of time. Is the light emitted by the object changes as a function of time? Or how much light is it emitting at this wavelength versus another wavelength? And the relative amount of light object emitted by that object at different wavelengths will give you an understanding of some property of that object. What is the polarization state of that light emitted by that object? Is the polarization state changing with time? Is the polarization state changing as a function of wavelength? And so on and so forth. So you analyze that light in various ways using imaging, spectroscopy, polarimetry, imaging polarimetry, spectropolarimetry, imaging spectropolarimetry. Whatever way you want to analyze that light, you analyze that, and that analysis of the property of the light emitted by that object is what is giving you information about that object. So a filter is used to cut down wavelengths outside what you are interested in. So you are observing a galaxy or sun or whatever, and you want to observe it at a certain wavelength. how much light is that object emitting around that wavelength. Then you use a filter to cut off all light outside that wavelength and collect, measure the flux, measure the brightness of that object at that wavelength. Then you put another filter, measure the amount of light coming from that object at that wavelength. And this relative brightness or other properties will allow you to study the nature of that object. So optical filters give you crucial information. There is no point collecting all the light coming from an object. You only know that, okay, that object is emitting this many photons total. Good. But you have no more information. On the other hand, if you know, okay, this object is emitting this many photons at this wavelength, this many photons at this other wavelength, you then try to understand what must be going on in that object, that celestial object, to make it emit this many photons at this wavelength, but only that much at this other wavelength. And to study that, you need optical filters. You can make filters in the lab. For that, you may be one good way is to just contact IUCAA. There are people in IUCAA who are can help you make simple filters for observations. So please be in touch with our public outreach or science popularization lab, where there are people who are able to make filters. The last question is, in a slide showing multiple mirrors focusing on single point, is there any interaction between images formed by individual mirrors? If yes, how to correct those? I'm not exactly sure. Yes, I think I understand what you're asking. If there are multiple mirrors used for producing an image like this, yes, the combined properties of these mirrors, this primary mirror, this secondary mirror, the combined properties of that mirror is what defines what is the effective focal length, what is the quality of the image you get, and so on and so forth. So there are prescriptions available, both in literature and online, etc., on how to design a Cassegrain reflector telescope. What are the properties? What should the primary mirror curvature look like? What are the parameters which define that parabolic surface? What are the parameters which define the ellipsoidal surface here, and how to achieve a Cassegrain reflector combination using a parabola and an ellipsoidal surface, and what is the advantage of that combination? This combination will have a different advantage. So depending on what kind of study you want to undertake, you would pick up the appropriate combination or pick up the appropriate prescription of making the telescope either Cassegrain or Maksutov or Schmidt Cassegrain, many other possibilities. And then there are prescriptions on how to design the optics and combine them in a way that it delivers the kind of performance you want it to deliver. Okay, so let me now switch to questions which might have come on YouTube. There are a few questions. So first question is what is the significance of ultra-azimuth and equatorial telescope? It is a little bit difficult to explain it as it is, but the main difference is in an ultra-azimuth telescope, the telescope structure has to move in along three different axes: the altitude axis, the azimuth axis, and then there's a third axis called the Cassegrain. So telescope structure has to move in synchronization in all these three axes to keep tracking an object in the sky. On the other hand, if the telescope is mounted in an equatorial mount, just by moving the telescope along one axis, you can keep tracking and you can track an object's movement in the sky. This is because the axis of the telescope as well is aligned parallel to the axis of the rotation of the Earth. Because they are aligned parallelly, just by moving the telescope around one axis, you will be able to track the movement of objects in the sky. So tracking is very easy in the equatorial mount system. On the other hand, in an alt-azimuth mount system, you have to track on 3 axes of the telescope to keep tracking an object in the sky. But mechanical fabrication-wise, construction-wise, alt-azimuth mounts are easier to make than our equatorial mount telescope. The alignments are easier to achieve, and the alt-azimuth mount telescope become compact physical structures compared to equatorial mount telescopes. So the modern trend is to mount telescopes in alt-azimuth mount because modern electronic control systems technology is so good that even though the alt-azimuth mount telescope has to track on 3 axes, you can achieve that by modern electronic control systems in synchronization to very high precision. And that is easier to achieve, but the advantage is that the telescope structure, the enclosure, etc. becomes more compact compared to an equatorial telescope. What is the focal length of the twin telescopes at Mauna Kea? That's the second question. As I said, each telescope very often have multiple focal length options. So by changing some mirror or some optical element in the telescope, you can change the focal length. So if you are referring to the twin telescopes, which are called the Keck telescopes, the 10-meter diameter, their standard focal length is 150 meters, which is what I mentioned in one of my first slides. So each of them has a focal length of 150 meters. And the diameter of the primary mirror is 10 meters. The next question is, in giant Magellan telescope, how the image from the different mirrors form a single image? This is a very interesting problem. It is a very difficult thing to achieve. So if you have a mirror, in order to form an image at its focal plane, what is required is that all the rays which are reflecting off the telescope, after passing through the either multiple optics or directly coming to the focal plane, they should have the same path length. So if you start a ray from one end of the telescope, one point on the primary mirror, trace it all the way to the focal plane, take another ray from any random another point on the mirror, trace it all the way to the focal length. The path lengths have to exactly match more fraction of the wavelength. So you know that the wavelength of light which we are interested in is about half micron. So if you are observing at a wavelength of half micron, the path lengths from each and every point on the telescope surface, starting from the telescope surface all the way through the optics of the telescope till it reaches the telescope's focal plane, the path lengths of each of these rays have to match a very small fraction of the wavelength. So if its wavelength is half micron, you want lambda over 10 or lambda over 20 of matching, which means that the things have to match to 25 nanometers. The path lengths have to match to 25 nanometers. In a single mirror, this is achieved by polishing the mirror to very high accuracy. That is why mirrors or glass is used. Glass can be polished to very high accuracy. And the surface of the glass is maintained to a fraction of the wavelength precision. It is polished to and figured and polished to a lambda by a small fraction of the wavelength precision. And it is not very difficult to achieve that on a single surface. But if, like the giant Magellan telescope which has 8 or 7 8-meter diameter mirrors, or the 30-meter telescope which has 500 individual mirror pieces, or the European extremely large telescope, which has 1,000 individual mirror pieces. It is not just enough to polish the individual mirrors, but you also need to make sure that the mirrors are mutually aligned to form the correct surface over the 30-meter area, which is, like as I said, in 20 nanometers. So if you have 500 pieces of glass, each of about 1.5 meters in size, each exquisitely polished to sub-wavelength polishing finish, then they are all arranged together, and they have to, in real time, be aligned and kept aligned to 25 nanometer mutual precision. That is a technological marvel, and that is a challenge in all these big telescopes. And today's technology hopefully will allow you to do that. The next question is, will there be uncertainty in photon collection for the telescopes orbiting above the sky? Yes, there will be uncertainty, except that when the telescopes are above the sky, whatever is the light which is scattered by the atmosphere does not reach your telescope, so that is good. But the sky still has some brightness. You look at any part of the sky, even from above the Earth's atmosphere, there will be some light, either zodiacal light or scattered starlight, light scattered by interstellar dust. There is some light. So that light will always be there as a background, even from space. And you have to account for that when you do those measurements. Now, the next question is it possible to change the focal length of this large telescope like twin telescope at Mauna Kea? The answer, as I said earlier, is yes. It is not an easy process. It is often a tedious process, but the telescopes in Hawaii, in these large telescopes, by changing the optics appropriately, can have different focal lengths. Not many, maybe many telescopes offer only one focal length, and that's fixed. Many focal telescopes offer more than one, maybe two, maybe three at the extreme cases. So 1, 2, or 3 different focal length options may be available, but not more than that. But it's a tedious process to change the settings very often. There is another question, what type of filter is used? Whether it is interference filters. Again, I don't fully understand that question, but let me try to answer that. Depending on the particular application, the type of the filter used would change. For example, if you are looking at what are typically called broadband filters, and they have typically a bandwidth of, or a full width at half maximum of about 100 nanometers. So you take 500 nanometer wavelength plus minus 100 nanometer bandwidth. That kind of broadband filters are not interference filters. They are just color glass or various kinds of colored filters. But if you really want to get down to extremely narrow wavelength filters, like filters which has 10 nanometers or 20 nanometers wavelength or smaller, then interference filters are often used. So when you are observing, let's say, an emission line, an object which emits a lot of light at a particular wavelength, a narrow wavelength band, and much less light at other wavelengths. So if there's an emission line and you want to observe that emission line, then you might need interference filters. And this is the last question, and we are running out of time. I need to stop. We are already quite a way beyond our time. So which type of telescopes are being used to observe planets in solar system? That again, as I answered before, the answer is not unique. Depending on what you want to see on the planet, do you want to see very fine details on the planet? Then you need a telescope which has very high angular resolution. But if you want to study something else, not in very high angular resolution details, but you want to cover a wide field of view to look for planets, then you might design a telescope with wider field of view. So if you are searching for planets, you might be using one type of telescope, but on the other hand, if you're trying to study the details of a given planet's surface or its properties, then you might use a telescope with very high angular resolution. So let me stop here because we are really over time. And I'm really happy to see all the very good questions. So keep firing those questions. And it was a pleasure talking to you today. And I'll talk to you again tomorrow, the same time. Bye for now.